Okay, welcome back. On to Chapter 3, I guess. So let's talk a little bit about Chapter 3. Of course, everything we talk about here is not on your first test, which is Chapters 1 and 2. It'll actually be on your second test, which is Chapters 3 and 4. So I guess let's get to it. All right, let's talk about chemical bonding. All right, there are three types of bonds that you run into in chemistry. You have what we call ionic bonding, you have covalent bonding, and then you have metallic bonding. Metallic bonding is bonding between metals. When you start mixing d orbitals into the picture, things get really complicated. You need something called molecular orbital theory to describe that perfectly. That is just not somewhere we're willing to go this semester. So we're not going to talk so much about metallic bonding, but the other two types of bonding you can talk about and you can describe with very simple theories and principles. So what is an ionic bond? Well, ionic bonds are electrostatic in nature. In other words, you've got something that's positively charged, you've got something that's negatively charged. Of course, we know opposite charges attract, and that's what keeps them together. That's an ionic bond. In a covalent bond, you have atoms that are sharing electrons, and what keeps them together is the fact that they're sharing the electrons. Both of these types of bondings really kind of have the same goal in mind. You're just achieving it in a different way, and we'll explain that as we go. All right. When you're talking about chemical bonding, particularly covalent bonding, but I guess ionic to a certain extent, it is useful to draw what are called Lewis structures or Lewis dot structures. And Lewis dot structures, what you do is you show the valence electrons. The valence electrons are the electrons that are available to be shared. It's not the total number of electrons an atom has, but it's the ones it's going to share. If you think about it, you've got your atom over here, you got another atom over here, and this is surrounded by electrons here. This is surrounded by electrons here. Well, if you're going to get them to react, you got to get them to touch. So where are they going to touch? Are they going to touch at the inner electrons or the outer electrons? Where they're going to touch at the outer electrons. So what Lewis, G.H. Lewis, I believe, not C.S. Lewis, that was a Christian writer, but G.H. Lewis said, well, you know what, really, you don't have to consider all the electrons in that case. What you can do is you can just look at the outer ones, and you can get a really good picture about how things are going to bond. And that's what we were talking about with distinguishing electrons in the last chapter, where we were looking at the last unfilled subshell. It's very similar. Same general idea. All right. So how do I know the number of valence electrons an atom has? Well, I guess I could write the electron configuration or do the orbital diagram and see where the outer electrons are, but maybe there's an easier way, and there is. All right. The number of valence electrons is equal to the group number the atom is in. It's that simple. So all you got to do is look at your periodic table and look at the group number. So for example, if I'm dealing with nitrogen, okay, nitrogen is in group 5, or remember 15. That's the numbering system we use here as well. If it's one of these, it's a 5, 5A, 6A, 6, 7A, just look at the number. If it's a teen, cover up the 1. So see, if I cover up the 1 on 15, I get 5. So see, you're going to get 5 either way. So nitrogen has 5 valence electrons. Now nitrogen has 7 electrons, but not all 7 of those are available to be shared. Only the outer 5. Essentially what it comes down to, it's the outer S and P electrons. So if you did the electron configuration for nitrogen, which I know you can by now, you'd see it's 1s2, 2s2, 2p3. Well, it's the 2s2, 2p3. Those are the 5 electrons that are available to be shared. But you don't even have to know that. All you got to be able to do is find the group it's in. And of course, you'll always have a periodic table on the test, so that should be fairly easy. Sulfur has how many valence electrons? Well, it's got 6, because it's in group 16 or group 6. See, it's got 16 electrons, but they're not all available to be shared. So that's how you tell the valence electrons. Just look at the group number the element happens to be in. It really is just that simple. Okay? All right, well, what about group 18? Remember group 18? That was a special group. Get back to my periodic table here. There we go. All right, or group 8. These are your noble gases. Remember, they were very stable. Okay. How many valence electrons do your noble gases have? Well, they have 8, see, because they're sitting there in group 8 or group 18. All right. And essentially, what that means is their outer S and P sublevels are full. We talked about this in the last video, I believe. How many electrons can I fit in an S subshell? 2. How many electrons can I fit in a P subshell? 6. What's 2 plus 6? 8. So there's your 8 valence electrons. All right, here's something called the octet rule. And the octet rule says if I can somehow get 8 valence electrons around an atom, then now it's got a noble gas top-like structure. It doesn't all of a sudden change into helium or anything, but it's got a nice noble gas structure, and if it's got that noble gas structure, it is chemically stable. All right? So what atoms want to do is they want to have 8 valence electrons just like your noble gases. Make sense? Okay? Keep that in mind. That might come up here in a couple of minutes. All right. Well, sometimes it's useful to be able to draw a Lewis symbol or a Lewis dot symbol. Okay, so how do you do that? Well, it's pretty simple. You write the symbol for the element, and then you just put the valence electrons around it. So, for example, if I wanted to do it for sodium, I'd say, okay, sodium. Where's sodium in the periodic table? What's over here? It's in group 1. So it's got 1 valence electron. So I'm just going to put 1 dot. That's it. Oxygen. Well, oxygen in the periodic table is over here in group 6, or 6A, 16, or 6A. All right, and so therefore it has 6 valence electrons. Now it's got 8 electrons, but only 6 of those are available to be shared. It's in group 6. You don't put the total number of electrons around the atom, you just put the valence electrons. All right, and so if I wanted to draw it for oxygen, I'd put an O here, and I'd put 6 dots. That's all there is to it. Okay, normally you kind of pair them up, so a pair here, a pair here, a pair here, and a pair here. I split these two. Did I do it for a reason? Yes, I did it for a reason. Does it matter when you're drawing the Lewis dot structure? No. You know, all I care about, I don't have super high expectations here. I'm kind of low maintenance. I want to see an O, and I want to see 6 dots. I really don't care how you arrange them. As long as I see an O and 6 dots, then you're going to be okay. All right, take a look at the periodic table, look at fluorine. Fluorine's over here in group 17. So that means it has 7 valence electrons. See? So I'm just going to put an L from with 7 dots around it. 1, 2, 3, 4, 5, 6, 7. And then carbon is in group 14 or group 4, depending on which periodic table you're using. So you're going to have 4 dots. Got 6 electrons, but again, look at the group number. Don't put the total number of electrons in there. Carbon has 4 valence electrons. So you're going to have a carbon, and you're going to have 4 dots around it. However you want to do it. Okay, again, there's a reason I split them up that way, but it's because I know something we'll talk about later. But yeah, I just need to see 4 dots. Can you do it? So basically, if you can count to 8, you can do Lewis dot structures. It's just that simple. All right. Well, how many atoms in the periodic table have 8 valence electrons? Well, this doesn't hang around very long. It's man-made. 1, 2, 3, 4, 5, 6. Helium, of course, is the exception to the rule. It only has 2 electrons. But, see, if you put 2 electrons around a helium, you filled up the first energy shell. That's 1s2. There is no such thing as 1p. So it's very stable. All right. So, generally speaking, group 18 has 8 valence electrons. Helium would only have 2. There's always an exception to the rule, isn't there? Seems like. Okay? How many of those atoms have that nice noble gas structure? Well, 6 that we know of, and this man-made doesn't hang around very long. By the way, element 118 has some stability associated with it. It hangs around for about 30 seconds, which, when when you get up that large with man-made elements, it's like an eternity. So yeah, there actually is some stability associated with element 118, but it's not anywhere near the rest of them. Okay, that's bonus information for you there. How many of them have that nice noble gas structure? Well, 6 of them do, right? What is everything else going to do? Because I got 112 other things. Well, I guess they're going to have to do something else. So I guess the question at this point is, what would that something else be? That's what we're going to talk about today. So, here's a bromine atom. How many valence electrons does that bromine have? Well, it's got 7. If you look at the periodic table, you'll see it's in group 17. So it's got 7 valence electrons. Is that 8? No, that is not 8. Is it close to 8? It's very close to 8. Is it close enough to 8? No, it doesn't work that way. You know, it's got to be 8 or nothing, right? What is that bromine going to do? Well, under certain circumstances, what that bromine will do is it will pick up an extra electron from somewhere. Where it comes from at this point, we're not too concerned about. We'll talk about that later. But it just picks up an electron from somewhere. All right. If it does that, now it's got 8 valence electrons, which is a good thing. Now it's got that nice noble gas structure. It is following what we call the octet rule. All right. So that's the plus. But is there a downside? Well, if I've got 35 protons with a charge of +1, now I have 36 electrons, just like krypton, which we know to be very stable. Is my bromine atom neutral anymore? Well, no, see, because it's got 1 more minus than it has plus. So therefore, it has a charge of -1. Is that good? Well, no. Here's something called the principle of neutrality. The principle of neutrality says, all things being equal, atoms and molecules prefer to be electrically neutral. All right? And basically, it's just a subset of all things being equal, atoms and molecules prefer to be in the lowest energy state possible. If you are neutral, you are lower in energy than if you have a charge. And the closer you are to neutral, the more stable you are. All right? And so that's really all the principle of neutrality really says. So I got 2 things going on here. I've got picking up the extra electrons, a good thing. It gives me a nice noble gas structure, which makes it more stable. And then I've got a negative charge there, which is a bad thing, and that makes it less stable. So I guess the question is, which one wins out, right? Well, the answer is it depends on where you are. In the open atmosphere, solids, liquids, low temperature gases have to be electrically neutral. They just don't exist. It's got to be neutral. So can I bring you a jar of bromide, which is what that is actually? No, I can't do it. It just doesn't exist as a solid, liquid, or gas. However, in a water solution, there's something about that water molecule that's able to stabilize that negative charge to make it less of an issue than it ordinarily would be. The fact that I have 8 valence electrons wins out. Can I bring you a water solution with bromide in it? Yes, actually I can. All right, and so this species is relatively stable. We won't take the relatively off here because you can't. This doesn't exist in open air. But yeah, in a water solution, I can have bromide floating around, no problem. And there's something about that water that's able to do that. What that is, of course, yeah, you guessed it. We'll talk about later. But we will get to it, trust me. It's just going to take a little while. All right. Well, likewise, here's a sodium atom. Sodium, if you look in the periodic tables in group 1, got your periodic table with you. I'll get an email here. So it's over here. Okay, so it's got 1 valence electron, right? Okay. Well, I guess it could pick up 7 electrons from somewhere, and that would give it 8 valence electrons. Do you think it's likely to pick up 7 electrons? What would the charge be if it picked up 7 electrons? It would be a -7. Do you think a sodium -7 would be very stable? No, you're just violating the principle of neutrality in a really big way. It's just not going to happen. What else could it do? Well, it could lose an electron. So it's kind of like an onion. You've got an onion there. You've got this little tiny piece of onion peel on it. And if you take that little piece and you scrape it off, what have you got underneath? Well, you've got a nice full onion skin underneath, right? It's kind of the same way with the sodium. If it loses an electron, now it's got a nice full shell underneath, and now it's got a nice noble gas structure, just like neon. See, had 11 electrons. Now it's got 10, just like neon, which we know to be very stable. So that's why sodium would want to lose one electron. Again, what's the downside? Well, the downside is if I've got 11 pluses for my 11 protons, and now I've only got 10 minuses, what's the charge on a sodium? +1. Okay? And so the upside is I've got the noble gas structure just like neon. We're not saying it changes into neon. The reason what makes neon neon is the fact that it has 10 protons, and sodium has 11 protons. But we're saying it has the same electronic structure as neon, which we know to be very stable. And so therefore that sodium plus is going to act chemically kind of like neon. Not exactly like neon, but it's going to be very stable. There's going to be some stability associated with it. All right? What's the downside? Well, it's got a charge. You're violating the principle of neutrality again. So can I bring you a jar of sodium plus? No. Solids, liquids, low temperature gases have to be electrically neutral. But there's something about that water molecule that's able to stabilize this positive charge as well, to make it less important, to make it closer to neutral. The fact that I've got the 8 valence electrons wins out. And can I bring you a water solution with sodium plus in it? Yes, I can. In fact, if you're drinking water right now, it's probably got some sodium plus in it. This coffee probably has some sodium plus in it. Okay? And in a water solution, it's somewhat stable. All right? So it's kind of one of these things. I've got advantages and disadvantages. Kind of depends on where you are. But the driving force here between these atoms losing electrons and gaining electrons is to try to get that nice noble gas structure, just like your noble gases. Because there's only 6 of them that have the noble gas structure. And the rest of the atoms are going to have to try to find something to do to stabilize themselves. This is one way. All right, notice that some of them are gaining electrons, some of them are losing electrons. If you've got a charged atom, so it's either missing or too many, these are called ions. Okay, charged atoms are called ions. Neutral atoms are called atoms. If your ion is positive, okay, in other words, it's missing electrons. Okay, now it's backwards here, because remember, an electron has a negative charge. So if you take away negative charge, you are becoming more positive. Okay, basically Ben Franklin back in the 1700s had a 50-50 shot of getting this right, and he messed it up. So yeah, that's why it is kind of the way it is. All right. So if you're missing electrons, your resulting anion is positive. We call that a cation, not a cation. It's a cation. All right. So cation is a generic term for positively charged ions, +1, +2, +3. All right. If your ion is negative, in other words, it has too many electrons. Electrons have a negative charge. So if you're adding negative charge to something, it's becoming more negative. We call those anions, anions. All right. So if we talk about the group 17 anions, it's just a generic term for saying all these negatively charged ions from group 17. Make sense? And that's kind of how it works. And it's either positively or negatively charged or neutral. I mean, those are the only 3 choices, right? So you have cations, you have anions. Okay. Well, let's say, for example, hypothetically, talked about sodium. Here's a potassium atom right here. What do you think a potassium atom is going to do? Well, let's see. It wants to have a noble gas structure, so there's a couple of things I could do. I could pick up 17 electrons and have 36 just like krypton. Do you think that's likely? No, probably not. Because if it picks up 17 electrons, now it's a potassium minus 17. No, no way. Really violating the principle of neutrality. What do you think's more likely? Picking up 17, or it could do what? We could lose 1 and have 18 just like argon. If it loses 1 electron, what charge is it going to have? It's going to have a +1 charge. What do you think is going to happen with rubidium? Well, it's probably going to lose an electron and have 36 just like krypton, and so it's going to have a +1 charge. Have you ever heard of rubidium before? Do you know anything at all about rubidium? You do. You know it forms +1 ions. How do you know that? Because of its position in the periodic table. And that's why the periodic table is so important. Even if you've never heard of a particular element before, you now know something about the chemical reactivity because elements in the same group react very similar chemically. See? That's why periodic tables are important to chemists. What do you think would happen with a cesium? Well, probably the same thing. Lose 1, have 54 like xenon. Do you see that all these elements in group 1, these are alkali metals, remember that, all these elements in group 1 all form +1 ions. Okay, we said they were chemically similar. Well, there you go. That's one way. All right. Well, let's take a look at magnesium. So what could a magnesium atom do? Well, it's got 12. It wants to have 18, right? So it could pick up 6. You think that's likely? Probably not. What do you think is more likely? Well, it could lose 2 electrons. If it lost 2 electrons, it would have 10 just like neon, right? What charge would it be if it lost 2 electrons? It would be +2, because see, you're getting rid of 2 negative charges, so you're becoming more positive. What do you think would happen with the calcium atom? Well, it'll probably lose 2 to have 18 like argon. How about strontium? Yeah, how about barium? Do you see that all these elements in group 2, your alkali earth metals here, do you see that these all form +2 charges? Because if they lose 2 electrons, now they've got a nice noble gas structure. Okay? Aluminum. Here's aluminum. What do you think is going to happen with aluminum? Well, it could pick up 1, 2, 3, 4, 5, or it could lose 1, 2, 3 and have 10 like neon. What do you think is more likely? Probably losing 3. So if it loses 3 electrons, what type of ion does aluminum form? It forms +3. Do you see what's going on here? Okay. Go all the way over here to group 17. What do we call group 17? Yeah, those are your halogens. It's right down here. Those are your halogens, right? All right. We talked about bromine, right? What do you think is going to happen with the chlorine? We could either lose 7 and have 10 like neon. Well, if it loses 7, it's got a charge of +7. Do you think a chlorine +7 is likely? No. Or it could do what? Gain an electron and have 18 like argon. Have a nice noble gas structure. So if it picks up 1 electron, what's the charge? -1. All right. Bromine, -1. Iodine, -1. Fluorine, -1. Each of these will pick up an electron to have a nice noble gas structure. Group 16, how about that oxygen? What do you think is going to happen? Well, I guess it could lose 6 or pick up what, 2? More likely to do what? Pick up 2. So if it picks up 2 negative charges, it was neutral, now it's got a charge of -2. So everything, sulfur, same thing, everything here in group 16 forms -2 charges. What do you think would happen with the phosphorus? Well, it could lose 5 or pick up 3, probably more likely to pick up 3. So what charge would nitrogen and phosphorus have as an ion? -3. See, because you're picking up a negative charge. That's why it's kind of opposite there. Make sense? Okay. What do you think would happen with an iron atom? Well, let's see. It could pick up 10 and be an iron -10. Likely? No, probably not. Well, let's see. It could lose, looks like it could lose 8, go from 26 to 18, and have a plus 8 charge. Do you think an iron plus 8 is likely? Probably not. You're violating the principle of neutrality in a really big way there. So iron probably doesn't form ions, right? Yeah. Plus 2, sometimes plus 3, mostly plus 3. Where did I get the plus 2 and the plus 3 from? Well, I just know it. Transition metals. These elements here in the middle, in this little gap, in this D block, and this F block technically actually is considered transition metals as well. The driving force behind them forming ions is different from the elements that we were talking about. Okay? The elements that we were talking about were on the edges of the periodic table, and so I can pick up or I can lose just a few electrons here or there, and I can get to a noble gas structure without having a really large charge. The driving force behind these elements, your transition metals forming ions, is different. It's not to get a noble gas structure. And that difference is something we don't want to explain at this point. So what do I need to know about transition metals for the future? Well, here's what you need to know. Number one, transition metals always form cations. In other words, transition metals always lose electrons. They don't gain electrons, generally. So they'll always be positively charged. Okay? And number two, transition metals can form multiple oxidation states. That term will make sense later on down the road. What it means at this point is it forms multiple types of ions. So iron can be plus 2 and plus 3 sometimes. Nickel is plus 2, sometimes maybe plus 4, not sure. Chromium can be plus 2, plus 3, plus 6. Zinc is always plus 2. We'll talk about that probably. But yeah, multiple types of charges. And you don't have to memorize all those multiple types of charges. No one's gonna make you memorize those charges. Right. There will come a day when I can give you a compound with one of those transition metals, and you can tell me the charge on that transition metal. But that's not right now. So just remember, transition metals, elements in the middle, different driving force behind forming ions. They can form multiple types of ions. They always form cations. If you can remember that, that's good enough for now. The rules apply for these on the edges because they can pick up or lose just a few, and they can get where they need to be. Now you'll notice I didn't do some more here. Why didn't I do more? Well, because sometimes there just is no rule. These pretty much always form plus 1, plus 2, plus 3, minus 1, minus 2, minus 3. When I give you rules, I try to give you rules that actually work at least 85% of the time. If I gave you a rule that worked 50% of the time, you could probably guess and get it right just as often as it was by memorizing my rule, right? And so, yeah, that's kind of the reason why. All right? Okay, well, if I can have atoms with a charge, is it possible to have molecules with a charge? Yes, actually it is. And these are called polyatomic ions. All right, poly means many, so polyatomic, many atoms. So you can think of polyatomic ions as kind of like a molecule with a charge. In your book on page 62, there is a table of common polyatomic ions. You need to memorize those. Okay, here's the thing. Anytime you go into a field, there's a certain amount of knowledge you just kind of have to have in your head. If you're a nurse, you just have to know certain procedures. You don't have to memorize everything. You don't have to memorize charts and charts of data, but you can't look everything up either. If you were a nurse and you had to look up everything you did on a shift, you'd never get work done. You'd be flipping through pages and this and that. There's just some things you got to know, right? And unfortunately, chemistry is kind of that way. There are some things that you just got to know. One of them are your common polyatomic ions. If you don't know your polyatomic ions, you're not going to be able to write formulas for compounds. You're not going to be able to name compounds, which is where we're headed here shortly. You're going to have a hard time balancing equations. You're going to have a hard time predicting results of chemical reactions. You just got to know them, unfortunately. And unfortunately, the only way to know them is just to sit down and memorize them. All right? So if you look at table 3.2, this is not table 3.2. This is table 7.3, but somebody's got my book. And this chart is pretty much the same as what you've got. I mean, your common polyatomic ions are pretty much what they are. So, yeah, we're about to close it up here on the video. But yeah, these are your common polyatomic ions. Okay? So, yeah, lots of these. You need to know the name, you need to know the formula, you need to know the charge. You might be thinking, oh my goodness, look at all these things, I'll never learn them. Well, here are some tricks to help you. It's not like 20 different things with, nothing to do with each other. Okay? Number one, you'll notice there's only one polyatomic ion in the entire chart that is positively charged. Everything else is an anion. Okay, and that would be NH4+. All right, this is your ammonium ion. All right, so you should remember that one because it's completely different than everything else. What the plus means is if you added up all the electrons a nitrogen and 4 hydrogens ought to have, and then you looked at the ammonium ion here, polyatomic ion, there's an electron missing somewhere, and that's why it's got a positive charge. Do you have to know where it came from? No. You don't have to know where it came from. You just have to know there's an electron missing, and that's why it's got a positive charge. All right? That one you should get because what's different from all the rest, right? So that one's already stuck in your head. All right? Another thing that can be helpful here, if you see 8 on the end of something, 8 means polyatomic ion contains oxygen. If you see an "ide" on the end of something, generally that means monatomic ion, atom by itself. So for example, a sulfide is just an S2- ion. But a sulfate is an SO4 2-. If you looked at all the electrons an SO4 ought to have, and then you looked at a sulfate, you'll find there's 2 extra in there somewhere. Do you have to know where they are? No. Are there places where they are more likely to be than others? Yes. Do you have to know that? Not right now. You just have to know a sulfate is an SO4 with a 2- charge, and it's called sulfate. A sulfide is an S2-. So ide usually means atom by itself, 8, polyatomic ion contains oxygen. All right? Now, it doesn't tell you how many oxygens, and it doesn't tell you the charge. For example, a sulfate is an SO4 2-. A phosphate is a PO4, but it's got a -3 charge. It's a different charge. Notice that all of these are either -1 or -2 except for this phosphate, which is -3. It's the only one that's -3. So see, this one ought to stick in your head, and that one ought to stick in your head. Wow. It's dark on me when I go that way for some reason. And the rest of them are your -1 or -2. So, if I don't know them and I got to guess, I'm probably guessing -1, -2. If you start guessing like -6, I know you haven't looked at this chart. Okay? But, I mean, right there you should know phosphate and ammonium because, I mean, they're different than the rest. I'd start there. Okay? Does 8 always mean 4 oxygens? No, it doesn't always mean that. Here's a nitrate polyatomic ion, and it's an NO3, and it's got a -1 charge. So 8 doesn't tell you how many oxygens, and it doesn't even tell you the charge. But it does tell you has oxygen, polyatomic ion. At least you got that going for you. Okay? Now, are there exceptions to the rule? There's always exceptions to the rule. For example, an OH with a -1 charge, that's a hydroxide. See? So it actually is a polyatomic ion. Cyanide, that's a CN-. That's one there as well. So, yeah, there's always an exception to the rule, unfortunately. That's just kind of the way it goes, right? Okay? Here's where it gets fun. If you see an "ite" on the end of something, what that means is 1 less oxygen than the 8, but the same charge. All right, so for example, here's a nitrate polyatomic ion. All right, you got an NO3 with a -1 charge. A nitrite polyatomic ion is an NO2 still with a -1 charge. See, a sulfate's an SO4 2 minus. A sulfite is an SO3 2 minus. Same charge, one less oxygen. So if you know your 8s, now you automatically know your ites. Of course, if you miss your ites, then if you miss your 8s, then you miss the ites. So make sure you know your 8s, I guess. All right. It gets more fun than that. If you see one less oxygen, or if you see a hypoite, that's one less oxygen in the ite, same charge. So for example, here's a chlorate. That's a ClO3 minus 1 charge. A ClO2 minus 1 charge is a chlorite. A ClO minus is a hypochlorite. All right? Going the other way, if you see one more oxygen than the 8, that's a perate. So a ClO4, one more than that, with a minus 1 charge is a perchlorate. So it goes perchlorate, chlorate, chlorite, hypochlorite. Do all of them have those? No. They don't all have those. But if you see an ite, just think one less oxygen in the 8, same charge. And that's one way you can kind of keep them straight. All right? Last thing here, and we'll probably cut this video. If you see hydrogen on the end of something, all right, the charge generally goes up by +1. So let's say, for example, I had a sulfate. Okay, of course, I know a sulfate's an SO4 2 minus. This is a hydrogen sulfate. It's an HSO4 minus. Okay, so when I put that hydrogen on there, notice my -2 went up to -1. All right, so yeah, same thing here, just the charge goes up by 1. A carbonate is a CO3 2 minus polyatomic ion. A hydrogen carbonate, sometimes known as a bicarbonate, but the hydrogen carbonate is fine, is an HCO3, and notice only -1. Your charge went up by 1. Okay, so for every hydrogen you see, your charge goes up by 1. Here's a phosphate, PO43 minus. A dihydrogen phosphate is an H2PO4. All right, I got 2 hydrogens there, so my charge goes up by +2. So a dihydrogen phosphate has a charge of -1, not -3. A hydrogen phosphate has a charge of -2. Are you going to get this in like 5 minutes? No, you're not. How do I know this? Well, I'm kind of used to it. Kind of been doing this for a while, right? Well, it's going to be the same with you. It's like speaking a foreign language. If you had high school Spanish 30, 40 years ago in rural Oklahoma, you probably don't speak Spanish very well. Okay, but if you lived in Mexico City last year, I'll bet you speak Spanish pretty well. Because if you didn't, you wouldn't be able to find the bathroom. You wouldn't find any food. Nobody'd feed you. So yeah, you probably have to speak Spanish. Well, it's kind of the same thing here. The more of this you use, after a while, they just kind of stick in your head, and you don't have to worry about it so much. But you got to start somewhere. So if it were me, I'd make myself some little flashcards. I'd put the formula on one side with the charge. I'd put the name on the other. And then look at the formula and say, okay, let's see, that is a Cr2O7. What is that? That's a dichromate. Okay, it's got a -2 charge. And then I turn them over and say, okay, acetate. What is acetate? Well, I think that's a C2H3O2, and I think it has a -1 charge. I guess it does. And then I just mix them up, and sometimes the name comes up, sometimes the formula comes up. You'd be surprised how quickly you can get these. So do the best you can. Take a look at those. Are these going to be on the test? Yes, these are going to be on the test. So yes, you do have to know these. This chart is not in your book. The chart you have in your book is pretty much exactly the same. So yeah, know the chart in your book. That's what I would be testing you on instead of this chart. I just don't have my book with me right now. I had to get it on the screen somehow. So your common polyatomic ions are pretty much the same, just about everywhere. Okay. All right. Well, I think we're running up on minute 40 here. So I think that's a pretty good place to stop. So we'll stop there, and I'll sit down and look at the notes, and we'll see if there's one more coming, but probably no more than one. If you don't see any more videos besides this one, I guess this was the last one, and we'll start here in class. But I'm thinking maybe we just do one short more and we'll probably call it good. So I guess I will see you next time. If I don't see you next time, I guess I'll see you in class when we get back. And of course, as always, ask any questions if you need to. More than happy to help you. You can email me. I'm watching. I'm around. Just out of town. So take care, and we'll talk to you later. So.